All right. This is the outline of today's session. Today we will discuss about factor analysis. Then we will focus on how to select appropriate statistical tests for particular types of data. And then how to get descriptive and inferential statistics, how to recognize and interpret the output from a statistical analysis, and finally, we will discuss on how to report a statistical output in a concise and appropriate manner. So let's get started. All right, we'll start with factor analysis today. Factor analysis is an exploratory data analysis method used to search influential underlying factors or latent variables from a set of observed variables. It helps in data interpretations. Why? Because it reduces the number of variables into some specific factors. It extracts maximum common variance from all variables and put them into a common score. So factor analysis is different from many other techniques as it is regarded as data reduction techniques or data summarizing using a smaller set of factors or components. So this is the definition of factor analysis. All right. We have two types of factor analysis. One is exploratory factor analysis. The other is confirmatory factor analysis, what we call as EFA and CFA. So EFA, it is the most popular factor analysis approach among social and management researchers. Its basic assumption is that any observed variable is directly associated with any factor. As you can see on this screen right side, you can see that in exploratory factor analysis, we don't know whether item 1 is related to factor A or factor B. Or maybe item 5 is related to factor A or factor B. So its basic assumption is that any observed variable like item 1, item 2, item 3, these items we call as observed variables or items. These are the items or indicators in our questionnaire survey. Okay, and these factors, okay, in the oval shape factors, they are, latent factors or unobserved factors. So these one are observed items or observed variables in order to measure these factors, factor A and factor B. Okay. While in confirmatory factor analysis, okay, as you can see on the left side, the basic assumption in confirmatory factor analysis is that each factor is associated with a particular set of observed variables. As you can see on this screen, factor A is associated, you see item 1, item 2, 3, and 4. And also factor B has, three items in order to measure factor B. This all comes from literature review, or maybe they are based on some theories. Okay, so that's why we call them as confirmatory factor analysis. CFA actually confirms what is expected on the basic. Okay, what is expected on the basic. But in EFA, we don't know which factor should be under which item should be under which factor. That's why we want to explore. Okay, that's why we call it EFA or exploratory factor analysis. EFA often used in the earliest stage of research to gather information about or explore the interrelationships among a set of variables. Okay, but CFA is a more sophisticated set of techniques that used later on in the research to test or confirm That's why is confirmatory factor analysis a specific hypotheses or theories concerning the structure underlying a set of variables. Okay, so the ovals in this figure, the ovals here represent unobservable or latent factors, whereas the rectangles represent observed items. They are our question, the question in our questionnaire survey, or the items in our questionnaire survey. All right. Move on. Okay, let's do an example together for better understanding. Okay, so our research model is like this, consisting of five variables, five main variables. But here, I just want to show you how to use factor analysis. Let's assume that we have 13 items, including 5 items for attitude, 4 items for subjective norm, and 4 items for perceived behavioral control. And we want to run factor analysis for these 3 variables. Okay, so let's get started. Let's open our material 2 dataset. I have already uploaded our material 2 dataset on eLearn. So it takes a few moments to open our SPSS. You can also open your SPSS and follow me, okay? So we want to run factor analysis with these 13 items. All right, let me open my material 2 dataset. Okay, so here is my material 2 dataset. Okay, now we want to run factor analysis, right? In order to run factor analysis, I have already included over here, as you can see here, you see, I have already included, step by step of doing factor analysis for you to refer back, okay? But let's do it together in SPSS. In order to do that, you need to click on Analyze, okay? And then you go to Dimension Reduction over here, okay? And then click on Factor. You can see this window, what their name is Factor Analysis. All right, so we have already 13 items, okay? So now we need to transfer all of those 13 items that we want to include in the analysis. All right, so the first 5 are under attitude, okay, we transfer, and then subjective norm, and then this one, perceived behavioral control, PBC. Okay, so we have already transferred all 13 items into this dialog box. Okay, and then next is you need to click on descriptives. Under descriptives, initial solution is ticked by default. Okay, but now I want you to tick coefficients, KMO, and also anti-image, and then continue. All right, next is extraction. Okay, this one is important actually. Extraction depends on the purpose of doing factor analysis, okay? The purpose of doing factor analysis. Under this extract, we have 2 options based on eigenvalue. Next is fixed number of factors, okay? Usually, when you are going to do factor analysis, I mean exploratory factor analysis, because you don't know, you are not sure how many factors are included, we don't know yet. Usually, we follow, the default option, which is based on eigenvalue. But in this example, because we know already based on our research model that there are 3 factors, and we want to use fixed number of factors. But usually we don't use this fixed number of factors. As we have 3 factors, we just tell the system that how many factors we have. we have three factors. Okay, so we tell the system that we have three factors, and SPSS will consider the analysis based on these three factors. Okay, so just click continue. And then next is rotation. Rotation, we usually use Varimax rotation, and then click continue. No need to do anything. Scores, no need. And options, click on options. Okay, we have here two options. Sorted by size is not important, it's up to you. And next is suppress small coefficients. Sometimes we change this absolute value from 0.10 to 0.3. Okay, so SPSS will remove the factor loadings less than 0.3. Okay, but in this example, no need to do anything. Okay, let's just just follow the default and continue. And then we need to click on OK button to generate the output. All right. Okay, so here are the output. The output generated by SPSS is quite extensive and can provide a lot of information about your analysis. Okay, so let's start with this KMO table, which is very important. This table actually shows two tests that indicate the suitability of your data for a structure detection. Okay, so KMO, actually, you can see that the value of KMO is over here, is 0.882, okay? So KMO returns values between 0 and 1. Let's look at, okay, yeah, over here. You see here, a KMO table shows, KMO value and Bartlett test. Okay, so KMO returns values between 0 and 1. A rule of thumb for interpreting the KMO value between 0.8 and 1 indicate the sampling is adequate, is very good. Okay, but values less than 0.5 indicate the sampling is not adequate and some actions should be taken. So values closer to 1 are better. So in this case, our KMO value is 0.882, which is greater than 0.5. Okay, it indicates that our sampling is adequate. Okay, so next is Bartlett test. Our Bartlett test should be, the significant value should be less than 0.05. Okay, so what is significant value in all tests after this? Okay, please keep in mind that significant value or p-value, what we call this p-value, if the significant value less than 0.05, okay, over here, less than 0.05, meaning that our test is significant, is meaningful, is significant. But if p-value is greater than 0.05, meaning that it is not significant. So in this case, yes, it is significant. Okay, so let's look at next table. Next table is correlation matrix, which is very important. Okay, in this correlation matrix, you need to look for correlation coefficients of 0.3 and above. As you can see that the correlation between the items, you see here, between the items in one specific factor is greater than 0.3. Okay, as you can see on this, red color rectangles. Okay, so all of them, they are greater than 0.3. But you can see that, okay, for example, PBC2 with SN1 is negative, or maybe it's less than 0.3. So meaning that it's not good that we put these two items under one single factor. Okay, they should be under two different factors. Okay, now next, okay, we need to know how many factors. if you just follow eigenvalue, okay, if you just follow eigenvalue, also you will understand based on this total variance explained table how many factors you have. Okay, how many factors you have. In this case, we already told the system that we have three factors. Okay, so we have also three factors over here. So each factor explains a percent of the total variance, even though we already told the system that we have three factors, but the contribution of each factor is good enough actually. Okay, so factors that do not explain much variance might not be worth including in the final model, but our values, percentage for all factors are good enough: 34%, 25%, and 25%, and overall 84%, or maybe almost 85%. So next, we need to look at rotated component metrics and also communalities. Okay, communalities actually. This communalities table gives information about how much of the variance in each item is explained. Low values, meaning that less than 0.3, could indicate that the item does not fit well with the other items in its component or in its factor. So the general guideline is all communalities should be above 0.5. So in our example, all communalities, they are greater than 0.5. All right, okay, now here also you can see that all of the factor loadings, they are high value, meaning that the first 5 items, attitude 1 to attitude 5, they create one single factor, and then over here these 4 created one single factor, and these 4 also will contribute to measure subjective norm. All right, now you see here this table actually shows sample size and factor loading, the relationship between sample size needed and factor loadings. Factor analysis is a technique that requires a large sample size. Okay, so it is based on the correlation matrix of the variables involved, and correlations usually need a large sample size. So acceptable factor loadings are related to the sample size. In this case, our sample size is 192, is almost 200. Okay, so our acceptable factor loading here is based on this table is 0.4, meaning that our factor loadings should be greater than 0.4. If we look at our rotated component matrix, we can see that all of factor loadings, they are greater than 0.4, meaning that they are good enough, okay, in order to be considered as a single factor. All right, so this is the table in report. We have concluded that, okay, so in conclusion, we concluded that there are 3 factors: attitude 1 to attitude 5. Okay, they contribute to measure one single factor, what we call it as attitude. PBC1 to PBC4, they contribute to measure PBC, and also subjective norm SN1 to SN4, they contribute to measure one single factor, which is subjective norm. Okay, so we also included the eigenvalue and also the variance over here. So this is the table in report, which is very important. Okay, you can follow exactly like this in your thesis or maybe in all your report research. Okay, so that's all about factor analysis. Let's move on to next tests. Okay. Data analysis, part one, univariate analysis, including descriptive statistics and summarizing data. Okay, what does it mean, univariate analysis? Okay, let me tell you that there are three types of analysis, which are univariate analysis, bivariate analysis, and multivariate analysis. So, what's the differences between univariate, bivariate, and multivariate analysis or statistics? Univariate statistics or analysis summarize only one variable at a time. Okay, we are dealing with only one variable at a time. Bivariate statistics compare two variables. Okay, compare two variables or maybe examine the relationship between only two variables. But multivariate analysis, we have more than two variables. We are dealing with more than two variables in um, multivariate analysis. Okay, so descriptive statistics have a number of uses. Okay, descriptive statistics. These descriptive statistics can be used in, for univariate or maybe sometimes bivariate analysis. Okay, so we use descriptive statistics. Why? Because we want to describe the characteristics of our sample. Okay, so the term descriptive comes from the word describe. Okay, we want to describe the characteristics of our sample, or maybe we want to check our variables for any violations of the assumptions underlying the statistical techniques that we will use to address our research questions. And last one is to address specific research questions. So sometimes we want to measure something, okay? So we should use descriptive statistics. All right. In order to run descriptive statistics, we need to go to analyze descriptives, as you can see over here, descriptive and also frequency and descriptives. Okay, we can use both in our descriptive statistics. Okay, so measures of central tendency. These measures of central tendency are, some terms that we can use them in our descriptive statistics. Okay, in our descriptive statistics. All right. So meaning that, sometimes researchers want to summarize the information about one variable into a single number. Okay, into a single number, what we call sometimes as mean or median or mode, something like that. Okay, so a measure of central tendency is a single value that attempts to describe a set of data by identifying the central position within that set of variable, within that set of data, actually. Okay, so they are classed as summary statistics. We want to summarize. Okay, we want to summarize the characteristics of our data into a single number or into a single value. Okay, so the mean, often called also average, is most likely the measure of central tendency that we are most familiar with, but there are others such as the median and the mode. So what is mode? The value that occurs most often in a data set. What is median? The middle number when numbers are arranged in order by size. What is mean? The average of the numbers. Okay, let's say we have variable gender. Okay, variable gender. Of course, we cannot use mean. Okay, maybe if we use mean. Okay, let's say we already coded gender 1 for male, 2 for female. Okay, let's say our mean is 1.2, 1.3. Can we interpret that? No, cannot. But for such variables, I mean categorical data, we can use mode instead of mean, okay? Because mean doesn't make any sense. If we use maybe 1.2, 1.3, whether it's male or female, we don't know. Okay, so we use more. For categorical, mean is not meaningful for categorical data, like occupation, gender, race, ethnicity, okay, whatever. Okay, now let's do some examples together. All right. Let's open our material 2 data set. The question over here is our sample representative? And is there any data entry error? Okay. Let's run this descriptive statistics for gender using our material 2 dataset. Okay, let me open my SPSS. All right, in order to run the frequency table, descriptive statistics, we go to descriptives, we go to frequency. We want to run for gender, okay? This one gender, so no need to do anything. You just press okay. All right. So this is the table, the table in the output for descriptive using frequencies. All right. So the question here is, as you can see on this slide, okay, it's exactly the same, right? You should also get the same result, okay? So you see here, the question here is our sample representative, yes or no? This table tells us out of 1922 respondents, 144 are male, and 48 are female. Okay, meaning that 75% of respondents are male, 25% of respondents are female. Okay, so in order to answer this question, is our sample representative, yes or no? We cannot say. Why? Because we should consider our population, because we are not familiar with the population under study. Okay, in this example, in your study, yes, of course, you know that you need to compare this percentage with the percentage of male and female respondents with the whole population. If the population breakdown, maybe we don't know. Maybe the population breakdown is also like this, 75%, 25%. If the population breakdown in terms of gender is 50%, 50%, 50% male consists of 50% male, 50% female, we can conclude that no, this sample is not representative, and you need to give some justification why this happened to your sample. Okay, so we cannot say that, because we need to refer to our population. You need to check your population, okay? And also, this is current position. So for categorical data like gender, like position, like occupation, like whatever, like this, okay, you can report like this. This one very important. You can use in your thesis, okay? So you see here, gender and position. We have frequency and we have percentage. No need to report this cumulative percentage or maybe valid percentage, no need. Okay, that's all. Frequency and percentage. You need to do this by yourself, okay? So this is all about our descriptive for categorical data, okay? For categorical data. Now, for categorical data, yes, we can use frequency and percentage, or maybe sometimes you can use mode. But whenever you have some, some continuous data, like age in years, okay, like age in years, like, our intention just now variable or actual variable, okay, whatever, like this, you need to run descriptive, and again descriptive, and we want mean, we want a standard deviation, and also sometimes we want skewness and kurtosis. I will explain to you later. Okay, so we want mean and a standard deviation over here. Okay, mean and a standard deviation. Let's do it together for age. Okay, is there variation in our data, and what is the level of the phenomena we are measuring? The level of phenomena that we are measuring can be measured using mean, The variation can be measured using a standard deviation. These two tables, okay? These two tables. So what is a standard deviation? Actually, a standard deviation, this is the table in report, okay? You can report mean and a standard deviation. A standard deviation measures the spread of a data distribution, okay? The spread of the data distribution. The more spread out a data distribution is, the greater its standard deviation. The standard deviation is a summary measure of the differences of each observation from the mean. Okay, in other words, it is a measure of how spread out numbers are. So, a standard deviation to 0 indicates that the data points tend to be close to the mean. Okay, the further the data points are from the mean, the greater the standard deviation. Okay, greater the standard deviation. Now let's move on to normality assumption, which are very important. Okay, normal distribution or a bell-shaped curve. Okay, the normal distribution is the most important probability distribution in statistics. I can tell you that. It's very important. The normal distribution is a probability function that describes how the values of the variable are distributed. Statistical analysis often have, dependent and independent variables, right? So many parametric tests, what we call them, parametric tests, okay, against non-parametric tests. Parametric tests, they are require that the data approximately normally distributed. Okay, so there are two terms that we need to check in order to assess whether our data is normally distributed or not. The first one is skewness, the second one is kurtosis. Skewness is a measure of symmetry. Okay, as you can see over here, okay, we have positively skewed distribution. We have negatively skewed distribution, but this one is normal distribution, okay? The black color, this bell-shaped curve, this black color shows a normal distribution. This one is skewed. This one is also skewed, that we don't like, okay? We want to be like this, okay? Our data, we want to be like this. So skewness is a measure of symmetry, and kurtosis is a measure of whether the data are heavy-tailed, like this one, heavy-tailed, or like light-tailed, okay? So relative to normal distribution, that is data sets with high kurtosis tend to have heavy tails or outliers, like this one, okay, or outliers, the green color one, okay? So data sets with low kurtosis tend to have light tails or lack of outliers. So a uniform distribution would be the extreme case, a uniform like this black color curve, okay? So the histogram is an effective graphical technique for showing both the skewness and kurtosis of datasets. So let's look at an example, and we want to run the central tendency for the variables delivery speed and price level on Hecto SPSS dataset. I have already uploaded this dataset on eLearn. Let's open our Hecto dataset. All right. So, okay, I opened already the Hecto dataset. The question is that run the central tendency for the variables delivery speed and price level. Okay, delivery speed. Let's go to SPSS. Okay, here is SPSS. We need to go to analyze. We need to go to descriptive statistics, and then we need to go to descriptives. All right. Now I cannot see whether which one is my, this one, delivery speed. Okay, delivery speed. Let me tell you how to see that. You just right click over here on this box. You can see that display variable names or display variable labels. I just select display variable labels. You can change it like this, okay? Display variable labels, right? So now we want delivery speed, right? Delivery speed, and then, sorry, we need to go to analyze, we need to go descriptive, and we need to go frequency, okay? Here is like this, delivery speed, okay? And then we want, as has been asked in our question, we want to include normal curve on histogram. Okay, normal curve on histogram. Where is that? You need to go to charts. You need to go to histogram, and you need to select this one, and you tick show normal curve on histogram, and then continue. Okay. So one more time. We go to analyze, we go to descriptive, we go to frequency. Why? Because we need chart over here, okay? We need chart. So you right click to display variable label. We want delivery speed. Then we transfer to this variable dialog box. And then we go to charts. We select histogram, and then we tick show normal curve on histogram. Then click continue. You need to go to statistics. You need to tick mean. You need to tick standard deviation, and also we want skewness and kurtosis values as well. All right, and then click continue. Then OK to generate the output. All right, so this table, the first table is a statistics table. You can see that mean value is 3.5 over here. A standard deviation is 1.3. And then skewness and kurtosis values are also here. Skewness is negative 0.085, kurtosis is negative 0.511, which is less than positive negative 1.96. Okay, remember here, to test the assumption of normal distribution, skewness and kurtosis should be within the range of positive negative 1.96. Okay, so this is within the range, the output, okay, refer to the output, we can see that our skewness and kurtosis are within the range. So based on this skewness and kurtosis value, we can conclude that our variable, just now this one, delivery speed, is normally distributed. But we want to check based on the chart also. You see, based on this histogram, as you can see here, yes, it is normally distributed, as you can see using this bell-shaped curve. It's not skewed, right? It's not positively or negatively skewed. So we can conclude that based on this histogram or based on skewness and kurtosis, our delivery speed variable is normally distributed. Okay, is normally distributed. So let's move on to our PowerPoint. Okay, so that's all about univariate analysis. So in univariate analysis, sometimes you need mode, sometimes you need just frequency and percentage, and sometimes you need mean and standard deviation, skewness, and kurtosis, depending on your question and also the nature of your variable. Okay, so that's all about univariate analysis. Next is bivariate analysis. Okay, bivariate and multivariate analysis. All right. In bivariate and multivariate analysis, we are looking for two things. Sometimes we are looking for relationships between variables. Sometimes we are looking for differences, or what we call that as comparison. Okay, comparison. Okay, so as we have just discussed earlier, bivariate analysis explores the concept of relationship between two variables, whether there exists an association and the strengths of that specific association or relationship, or whether there are differences between two variables and the significance of these differences. So bivariate analysis can be helpful in testing simple hypotheses of relationships or differences. Okay? But multivariate analysis is the statistical analysis of many variables at once. Many problems in the analysis of life and social sciences are multivariate in nature, right? They are more than they consist of more than two variables. So what we call them as multivariate analysis is just an extension of bivariate analysis, in which two or more independent variables are taken into consideration simultaneously to predict a value of a dependent or more than one dependent variable for a specific subject. Okay, so these are the differences between multivariate and bivariate analysis. Okay, here is very important. Okay, this slide and the next few slides, they are very important. I just summarized how you can select your statistical test. This is just an overview of different statistical techniques, and later on we will go through some examples on these tests. Okay, please pay attention to this part. Okay, first one is whenever we're going to explore the relationships among variables. Okay, whenever we are going to explore the relationships, okay, actually there are two main there are two main purpose of doing a statistical analysis. One is the relationship. We want to examine the relationship between or among some variables. Next is we want to explore the differences between some groups. The first one, whenever you are going to explore the relationship among some variables, such as between age and satisfaction, your question can be, is there a relationship between age and satisfaction? Okay, but whenever you are going to explore the differences between groups, or you want to have some comparison between groups, male, female, older, younger, okay, such as age consists of older and younger groups or categories, you are looking for some differences in related to some dependent variable. Okay, maybe in this case, in our example, is satisfaction. So the question is, are older people more satisfied than younger people? Look at this. In both examples, we have age and satisfaction. Over here also we have age and satisfaction, but they are totally different. The first one, we should run correlation test. Why? Because we are looking for relationship. Here we should run t-test. Why? Because we are looking for some differences between two groups of people, older and younger. Depends on measurement scale of your variables, and also what is the purpose of your question. I mean, the question is related to relationship, or you are looking for some differences. The tests are totally different. Okay, now you see here, whenever you are going to explore some relationships, you can run Pearson or Spearman correlation. So Pearson or Spearman correlation is used when you want to explore the strengths of the relationship between two continuous variables. Okay, we will have some examples on this. No worries on that. Okay, you just pay attention to the terms that I'm discussing about. So if you are looking for some relationship, you can run Pearson or Spearman correlation. And your variables are continuous variables. You have two continuous variables and you are looking for relationship. Okay, you can run experimental or Pearson correlation. Factor analysis, as we have just discussed, allows you to condense a large set of variables down to a smaller, more manageable number of factors. This technique is often used when developing measures to identify the underlying structures or factors. You want to know how many factors. Maybe you have 20 items. You want to know these 20 items are measuring how many factors, or maybe are contributing in order to measure how many factors. You run factor analysis. It's a still relationship. We also have linear regression and multiple regression. Linear regression attempts to model the relationship between two variables by fitting a linear equation to observed data. One variable is considered to be an explanatory variable or independent, and the other is considered to be a dependent variable. So in linear regression, we have two variables, one independent and one dependent variable. The scale should be continuous over here. Okay, continuous. Next is multiple regression. It is a more sophisticated extension of correlation and is used when you want to explore the predictive ability of a set of independent variables, meaning that more than one independent variable. You have 2 or 3 or 4 independent variables on one continuous dependent variable. You should run multiple regression. Okay, so this is the differences between linear and multiple regression. Right. The other purpose of the study is maybe your purpose of the study is exploring differences between groups. Okay, between or among groups. We have t-tests or we have one-way ANOVA. Okay, t-tests are used when you have only two groups, males, females, younger, older, or two sets of data, before and after. And you wish to compare the mean score on some continuous variables. Okay, on some continuous variables. One-way analysis of variance or ANOVA. Analysis of variance techniques are used when you have more than two groups and you wish to compare the mean score on a continuous variable. It is an extension of t-test. In t-test, we have only two groups, male, female. In one-way ANOVA, we have more than two groups, like ethnicity. Malay, Chinese, Indian. We have three groups, right? So we need to run one-way ANOVA in that case. Okay, if the categories consist of more than two groups. Okay. Now, I want you to think and answer this. Explore the association between pairs of variables. Think about this. Okay. If you want to explore the association between pairs of variables, just now we have mentioned already that you need to run correlation, right? You need to run correlation because you're looking for some association or relationships between variables. Okay. You want to predict scores on one variable from scores on another variable. You only have one dependent and one independent variable here. So you should run linear regression, right? Linear regression. Next, you want to predict scores on one dependent variable from scores of a number of independent variables. So this one should be multiple regression or multivariate regression. Okay, multivariate regression. Okay. Next, the last one is identify the structure underlying a group of related variables. This one is factor analysis, right? Factor analysis, we have already discussed earlier about factor analysis. So this is how you can understand that which test is suitable for your research question. You need to see whether you are looking for some relationship between variables or you are looking for the associations between, comparison, or to see the differences between variables. Okay? Now let's move on to exploring relationships among variables. The first one is chi-square of independence or chi-square test. Okay, maybe you have heard already chi-square test. Chi-square test is used. This slide is very useful. Okay, I try to make, similar slides for, different tests. Maybe later on, once you want to select your test, okay, your test, or maybe the type of the analysis, you can refer to these slides because everything is inside. You see here, I have already mentioned one categorical IV, one categorical DV. So meaning that for chi-square test, you need one categorical IV. IV means independent variable, DV means dependent variable, and one categorical DV. Okay, so chi-square test is used to discover if there is a relationship between two categorical variables. You have one IV and one DV. Okay, so this is chi-square test. In order to run chi-square test, you need just now I have mentioned already. You need two categorical variable. And you need to go to analyze. You need to go analyze descriptive statistics, and you go to cross tab. Okay, you go to cross tab. Once you go to cross tab, you can open, to cross tab. You can see this window. Okay, you can see this window. In this window, you just tick chi-square test. Okay. You just tick chi-square test. Okay, whenever you open cross tab, you can see, a statistics button. You just, click on the statistics button. You can see chi-square. You need to tick this. Okay, you need to tick this chi-square test. So the chi-square test for independence, also called Pearson's chi-square test or the chi-square test of association, is used to discover if there is a relationship between two categorical variables. Okay. Here is an example of chi-square test. And also, this is how you can report the result of your chi-square test in APA style. Because USM follows APA style, whenever you are going to report your analysis, whether you are qualitative or quantitative, you should follow those APA style. This is very important and is very, very useful for you, okay? So you see here, is level of intention dependent on gender? The question here is level of intention dependent on gender? In gender, we have two categories only, male, female. Intention also, we have two categories, high and low. So we have two categorical data over here. That's why we can run chi-square test. Once you run chi-square test, this one is just descriptive or crosstab table. Just descriptive or crosstab, okay? But this one is very important. This table, this chi-square test table is very important. You need to look at this significant value. If your significant value is less than 0.05, meaning that, yes, there is a relationship between intention and gender. If this one is, this p-value or significant value is more than 0.05, meaning that no, there is no relationship between these two variables. But in this case, yes, there is a relationship between the two variables, and this is how we can report chi-square. One is degrees of freedom we got from here, and also equals, this one is the value of chi-square, our chi-square 8.934, and you need to report also your p-value. P-value is 0.003. Okay, so this is how you can interpret the output of your chi-square. Okay, I try to include, two different tests, and to show you how to report if your chi-square test is significant, like this example, and if your chi-square test is not significant. So this table, as you can see here, this is not significant. Why? Because it is more than 0.05, right? So it's not significant. You need, okay, whether the results are significant or are not significant, you need to report. You cannot just do nothing if the result shows non-significant. Okay, if your result also non-significant, you need to report. You see here, this tells us that there is no statistically significant association between gender and preferred learning medium. That is, both males and females equally prefer books versus online learning. And this is how you can report your chi-square. Okay, this one is not significant. In this example, is significant. And I'll show you how to report. Okay, now let's do it together. Let's do an example together. What is the relationship between education and current position using material 2 dataset? Okay, all right, let's go to material 2 dataset. So the question here is education and current position. Okay, education and current position. All right, let's go to our material 2 dataset. In order to do that, we go to analyze, we go to descriptive, and then we need to go to crosstab, right? We want education and current position. Education and current position. Okay, so one of the variables we just, transfer into row. The other one we transfer into column. Okay, the other one we transfer into column. Then we just click on this statistics, and then we take this chi-square. Okay, chi-square, and then continue. In cells also, you can maybe select row, column, and total. This shows the percentage. This is just descriptive. Okay, descriptive information. Okay, shows further details. All right, and then we just click OK. And then let's look at the output over here. This one is the table, the crosstab table. Is descriptive, but now let's look at the result. Our Pearson correlation is significant, so we can conclude that yes, there is a significant association between them. All right, so here I already included that. You see here, there is a statistically significant association between education and current position, and this is how you can report your chi-square. Okay, your chi-square. So you need to include one, square over here. Okay, I forgot to include that. All right, so let's move on to next test, which is correlation. Okay, so this is all about our chi-square. Okay, exploring relationships among variables. Next is Pearson correlation. So Pearson correlation is a measure of the strength and direction of association that exists between two variables measured on interval or ratio scales, meaning that we have two continuous variables over here. Okay, so we have two continuous variables over here. So the research question in correlation can be like this. Is there a relationship between age and optimism scores? Okay, or does optimism increase with age? If your data is normally distributed, you can select Pearson correlation. You can go for Pearson correlation, what we call that as parametric test. But equivalent non-parametric test of Pearson correlation is Spearman correlation. So you need to check the kurtosis and skewness before you run your correlation. Okay. So How can we determine the strengths of association based on the Pearson correlation coefficient? Okay, here are the answer. Actually, the Pearson correlation, the correlation value is between 0 to 1. Is between 0 to 1. So 1 is perfect relationship. Okay, so you see here, so as you can see over here, based on Cohen, if your R or Pearson correlation is between 0.1 to 0.29, or maybe less than 0.3, you can conclude that there is a small correlation between variables. If it's between 0.3 and 0.5, you can conclude that there is a medium correlation between two variables. If it's greater than 0.5, the correlation is greater than 0.5, you can conclude that there is a very large or good or adequate relationship between two variables. If 0, you see here, meaning that there is no relationship between variables. But you see here, R equals 0.7. It's like this, it shows like that. Okay, so this is how you can interpret the output of your Pearson correlation. In order to run Pearson correlation, you need to go to analyze, you need to go to correlate, and then Multiwrite. Okay, and then Multiwrite. In Multiwrite, okay, let's say we have two variables over here. We have height and jump distance. Okay, height and jump distance. So the default is Pearson. If the data is normally distributed, which is the case in this example, okay, so no need to change anything. You just click OK. So this is the output. This is the output correlation table or correlation matrix. What we call that as correlation matrix. In this example, we need to check significant value. If significant value or p-value less than 0.05, meaning that your correlation is significant and there is a significant correlation between the two variables. Okay, in correlation table, if there is a stars, 1 or 2 stars on your Pearson correlation value, meaning that this is significant. If this one more than 0.05, there won't be any SR over here. So with these SRs, we can understand that correlation is significant at 0.01 level. Okay? So in this example, we can see that the Pearson correlation coefficient R is 0.777 and that this is a statistically significant and P is less than 0.05. Okay, so this is the correlation, and here is how you can report in your thesis. Okay, this is the API style correlation symbol is R. Okay, P less than 0.05. A Pearson correlation was run to determine the relationship between an individual's height and their performance in a jump distance. Okay, so the data showed no violation of normality. You need to check before you run the correlation. There was a strong positive correlation between height and distance jumped, which was statistically significant. Okay, so this is how you can report in your thesis or in your publications. Okay. So this is all about our correlation. Let's do a hands-on activity together using materials to dataset. Okay, materials to dataset. We want to see if there is any correlation between attitudes and actual sharing. Okay, let's open our material to dataset. We go to analyze, we go to correlate, we go to Multiwrite. Okay. Based on our previous session, I teach you already that how you can compute once you run reliability test. If alpha value is greater than 0.7, you can compute in order compute that specific variable to create a single score. a single score for that specific variable, just like, attitude, subjective norm, intention, like that. All right, so we have, let's select all variables over here. We have attitude, subjective norm, intention, PBC, and share. Okay, and we know that all of our variables are normally distributed. Okay, and we just, we don't, so no need to change anything because this Pearson is by default tick already. Then we just click OK. Let's see the output. All right, the output is like this. You see here, the output is like this. Okay, so how we can report this correlation matrix in our thesis is like this. You see here, you need to remove the duplicate top half. The correlation matrix is symmetrical about the diagonal. Okay, so the top half is redundant as it reflects the same information presented on the bottom half. So you need to remove that and you just include those things. You can also include the stars over here. One star indicates your p-value is less than 0.05. 2 stars indicates that your p-value is less than 0.01. So this is how you can report your correlation matrix in your thesis. Okay, that's all about correlation. Let's move on. Next test, which is exploring differences between groups. All right. First one is one sample t-test. Okay, one sample t-test. Let me tell you that there are 3 types of t-test. The first one is one sample t-test. The second one is independent sample t-test. The third one is paired sample t-test. Okay, so in statistics, t-tests are a type of hypothesis test that allows you to compare means. They are called t-tests because each t-test boils your sample data down to one number, which is t-value. Okay, so t-tests are a statistical hypothesis test that analyze one or two sample means, average mean. Okay, when you analyze your data with any t-test, the procedure reduces your entire sample to a single value, which is t-value. Okay, so one sample t-test is used to determine whether a sample comes from a population with a specific mean. The population mean is not always known, but is sometimes hypothesized. Okay, so for a one sample t-test, there will only be one variable's data to be entered into SPSS Statistics, the dependent variable, and also we need to have population mean, meaning that in one sample t-test, we just need one continuous dependent variable and population mean. What is independent sample t-test? The independent sample t-test compares the means between two unrelated groups, males, females. Okay, two independent groups on the same continuous dependent variable. It measures the significant difference in the means of the two categories or two groups. So this is the definition of independent sample t-test. But what is paired sample t-test? The last one is paired sample t-test. A paired sample t-test is used to test if an observed difference between two means is statistically significant between two means, meaning that whether there is a significant difference between the average values of the same measurement made under two different conditions, before and after. You only have one variable, but you will measure twice in two different conditions. before and after. So in that situation, you need to run paired sample t-test. All right? Okay. Let's start with one sample t-test. So your dependent variable should be measured at the interval or ratio level, should be continuous. Examples of variables that meet this criterion include maybe IQ or maybe exam performance, whatever, all of your continuous variables. In order to run one sample t-test, okay, you need to go to analyze, you need to go to compare means, and one sample t-test. Select one sample t-test. You can transfer your dependent variable, your DV, into this test variable dialog box, okay, and then you need to define your population mean, okay, in this case is for population mean, and then just click OK. This is how you can interpret the output. The first table is one sample statistics, okay, one sample statistics. This shows that mean depression score is 3.7. Your standard deviation value is 0.74, was lower than the population normal depression score of 4, because your mean is 3.7, which is less than 4, right? Is lower. So the next table shows one sample test, which is important, more important than that. That one is also important, but it's just descriptive. But this one shows the significant value, the significant level. So you need to look at this column, which is significant level. If less than 0.05, meaning that your test is significant. If more than that, it's not significant. So in this case, yes, it is significant. Depression score was statistically significantly lower than the population normal depression score. This is how you should report. Okay, don't forget. This is how you should report your one sample t-test. Okay. Next is independent sample t-test. Okay, in independent sample t-test, you will have one categorical IV, including two groups only: gender, male, female, high, low. Okay, two groups only, and one continuous DV. So independent sample t-test compares the means between two unrelated groups on the same continuous dependent variable. Okay, on the same continuous dependent variable. Alright, now your dependent variable should be continuous scale. As we have mentioned many times, your independent variable should consist of two categorical independent groups. So your research question can be like this: are males more optimistic than females? Right? Because we want to have comparison between males and females. Okay? So the equivalent non-parametric test of t-test is Mann-Whitney U-test. Okay, Mann-Whitney U-test. If your continuous variable is not normally distributed, so you can go for equivalent non-parametric test, okay, which is Mann-Whitney test. All right, so in order to run t-test, you need to go to analyze, you need to go to compare means, and then you need to go to independent sample t-test. Independent sample t-test. You just transfer your DV into this dialog box, test variable, and then grouping variable, you need to define your grouping variable over here, define group, okay? Once you click on this define group, this will pop up, okay? This window will pop up. So you have two groups, right? 1 and 2, and then click continue and click OK. This is how you can run your independent sample t-test. Okay, let's look at this example. Okay, does intention to share vary by gender? Let's do it together, okay? Does intention to share vary by gender? This one is using material to dataset. Let's go to our SPSS. We want to run independent sample t-test. So the question over here is, does intention to share vary by gender? So we have gender and we have share, okay? So let's go to SPSS. We go to analyze. We go to compare means. We go to independent samples t-test. Okay, so our dependent variable is share, right? Let me check one more time. Is intention to share, is intention. So it's intention. Our grouping variable is gender. Let's select gender and transfer over here. Then we need to define our groups 1 and 2. Continue. Okay, and then click just OK. All right, so we have two tables. One is descriptive table and the other is independent samples table. Okay, independent samples test table. All right, here. The first one is descriptive and this one is important. You need to look at your 11th test first. If your 11th test is significant, meaning that the p-value is less than 0.05, you need to read second row, which is equal variances not assumed. But if your 11th test is not significant, which is the case in this example, is more than 0.05, you should consider equal variances assumed. So you need to read first row, which is over here. Okay, which is over here. So meaning that our test is significant. And our t-value is 3.122. Okay, so this is how you can report. An independent sample t-test was conducted to compare if there were differences in intention to share between males and females. The intention to share was higher among males, you see here, because mean value for male is 3.9, for female is 3.5. Okay, the intention to share was higher among males. You can report mean and standard deviation than females. Also, you can report mean and standard deviation, and a statistically significant difference is like this. You see t value, and in the bracket you need to put your df. Your df is 190, 3 point something. Okay, this one is t value, and also you need to report your p value. So this is how you can report. You should get the same results, the same output. Okay, you try to run this test using your material to dataset. Okay, so this is just an example of non-significant. I just want to show you how to report. An independent sample t-test was conducted to compare the self-esteem scores for males and females. So there was no significant difference in scores for males and for females. You also need to report your the mean value for male and female. Okay, so this is how you can report if your independent sample t-test is not significant. Okay, so next is still exploring differences between groups. One-way ANOVA. Okay, one-way ANOVA. One-way ANOVA is used when we want to compare a continuous variable across more than two groups, which are also called the between groups test. In one-way ANOVA, you have one categorical IV with more than two groups, and you have one continuous DV. Okay, you have one continuous DV. So maybe you ask, why not compare groups with multiple t-tests? Okay, why not compare groups with multiple t-tests? Because every time you conduct a t-test, there is a chance that you will make a type 1 error. Okay, this error is usually 5%. Okay, by running two t-tests on the same data, you will have increased your chance of making a mistake to 10%. So this is not acceptable. And ANOVA controls for these errors so that the type 1 error remains at 5%, and you can be more confident that any statistically significant result you find is not just, running a lot of tests. Okay, it's like that. So it's better than running, few more times t-test. Okay, let's look at some description of one-way ANOVA. The one-way analysis of variance is used to determine whether there are any statistically significant differences between the means of three or more independent groups, like ethnicity, like occupation, like this. The one-way ANOVA compares the means between the groups you are interested in and determines whether any of those means are statistically significantly different from each other. If the one-way ANOVA shows a statistically significant result, this indicates that there are at least two group means that are statistically significantly different from each other. Okay, so cross-Wallis test is non-parametric equivalent of one-way ANOVA if your DV is not normally distributed. Okay, in order to run one-way ANOVA, you need to go again to analyze, to compare means, and you select one-way ANOVA. In this table, you can, transfer your DV into dependent list, your IV, which is your grouping variable, into this one, okay, over here, this factor box, and then you can click on post hoc test, okay, post hoc test, and then you just choose to key, and then click continue. Okay, then you can see the results. You can do this at home using your material 2 dataset. The question here is, does intention to share vary by position? Let's do it together. Okay, you just follow me. We go to analyze, we go to compare mean, and then we go to one-way ANOVA. Then our intention is our DV. Our DV is intention. Our factor is occupation, right? Is position. All right, so position, we select position and we put over here. And then we go to post hoc. We just select cookies test. We cannot select more than one test for post hoc test. Okay, we cannot select that. So we just select our cookies test. Then we click continue, and then in the option you can select descriptives, and yeah, that's all. Then click OK, and then OK. All right, this is descriptives, ANOVA table, and post hoc. Okay, and post hoc and cookies test. All right, let's start with descriptive table. In our descriptive table, you can see mean and standard deviation for each categories. 1, 2, 3, 4, 5. We have 5 categories under position. Okay, so you can see mean and standard deviation over here. Okay, next is test of homogeneity of variances. You can tick this one as well. Test of homogeneity of variances. Let's look at the output. One more time, we go to one-way ANOVA. We can select in option, we can select homogeneity of variance test as well, and then continue. Yes, all right, over here. All right, so for intention, we have descriptive, all right, we have descriptive, and we have test of homogeneity of variances. If this one is significant, okay, if this one is significant, meaning that homogeneity of variances was not violated, so you don't have to worry on that. Okay, no need to be worried on that. And then next is ANOVA table. You need to look at ANOVA table. If this significant value is less than 0.05, meaning that your ANOVA test is significant. Okay, meaning that there was a statistically significant difference between groups as determined by one-way ANOVA. This is how you can report in APA style, meaning that F, you need to consider like this. F 4187 you need to get from the f over here, and this f value is 5.2, okay, and your p value is less than 0.05. This is all you will need to write for the one-way ANOVA. However, in reality, you will probably also want to report means and a standard deviation like this one, okay? Means and a standard deviation for your groups, as well as follow up a statistically significant result with a post hoc test. In this case, we have already choose two case tests. Which post hoc test should I use? Okay, which post hoc test should I use? There are a great number of different post hoc tests that you can use. However, you should only run one post hoc test. Do not run multiple post hoc tests, okay? For a one-way ANOVA, you will probably find that just two tests need to be considered if your data met the assumption of homogeneity of variances, like this one, okay? So you can use Toki's post hoc test. If your data did not meet the homogeneity of variances assumption, you should consider running the Games-Howell post hoc test. Okay, the Games-Howell post hoc test in your post hoc dialog box. Okay, so this is how you can report. All right, you still remember that I told you if there is a star over here, meaning that there is a significant differences, okay, a statistically significant differences, meaning that you need to find, the categories, those categories that they differ significantly. They differ significantly. That's why we run ANOVA, right? So the significant value over here, this one is significant between engineer and senior engineer, meaning that the mean value between engineer and senior engineer is significantly different. Okay, and also between engineer and above manager, between engineer and above manager, and also between manager and above manager. So this is how you can report. The one way between group ANOVA was conducted to test whether intention to share differed by position. There was a statistically significant differences at, p less than 0.05 level in intention scores for the 5 position levels. You can report your F, okay, and then your F values, and then post hoc comparison using the Toki's test indicated that the mean score for senior engineers and above manager were statistically different from engineer. Okay, this is how you can report. Okay, this is how you can report. You can follow this, this interpretation. I mean, this report in your thesis. All right. So that's all about comparison between groups. So we talk about, some t-tests and also one-way ANOVA. We talk about correlation regarding the relationships between variables, and we talk also about vector analysis and exploring the relationships among variables. Linear regression is used when we want to predict the value of a variable based on the value of another variable. Okay, so we use linear regression when we want to predict the value of a variable based on the value of another variable. In here, we have two continuous variables. We have one IV and we have one DV. Okay, we have one IV and we have one DV. So linear regression is the next step up after correlation. It is used when we want to predict the value of a variable based on the value of another variable. Your two variables should be measured at continuous level. Here, you can see the equation of linear regression, meaning that y equals a, x plus b, okay, plus b. They follow this line, okay. This line shows this equation. So linear regression is the next step after correlation, and the variable that we are using to predict the other variable's value is called independent variable, or sometimes we call it as predictor. Okay, predictor. For example, you could use linear regression to understand whether exam performance can be predicted based on revision time and so on, okay? And many more examples. You can use regression. All right, so in order to run regression, you can go to analyze, linear regression, you can go to analyze, you can go to regression, and then you can go to linear regression, and then you can see this window, okay? Your dependent variable now is price, and dependent variable and independent variable is income level. Okay, so the question here is how much of the variance in DV can be explained by IV? Okay, can be explained by IV. And then you can click OK. Okay, you can click OK. In this regression, this table, the first table is model summary. The first table is model summary. This table provides R and R square values. The R value represents the simple correlation. Just now, okay, we had Pearson correlation, remember? This is R. R is just, just Pearson correlation, which is here 0.873, which indicates a high degree of correlation. The R square value indicates how much of the total variation in the dependent variable price can be explained by the independent variable income. In this case, is 76.2%. Okay, can be explained, which is very high. Okay, which is very high. Next table shows, this table indicates that the regression model predicts the dependent variable significantly well. How do we know this? You see here, look at the regression value, look at the regression row, okay, this one, and go to the significant column. This indicates a statistical significance of the regression model that was run just now, okay? So here our p-value is less than 0.05, which is, is like 0.00, which is less than 0.05, and indicates that overall the regression models statistically significantly predict the outcome variable, and it is a good fit for our data as well. Okay, our F value is 57.737. Okay, so this is how we can interpret the ANOVA table. And the last one, next table, is coefficients. And based on this coefficient table, we can develop our linear regression equation. So the coefficient table provides us with the necessary information to predict price from income, as well as to determine whether income contributes statistically significantly to the model by looking at the significant column over here. And we can see that yes, this is significantly significant. So the equation is like this: price is our DV equals our constant. The constant over here is 8287 plus the coefficient over here on a standardized coefficient times income. So this is the regression equation based on the coefficient table. Okay, based on the coefficient table. So that's all about our analysis. It's too much actually. I try to cover, the most important test in, using SPSS. Usually, students, PhD and master students, they use, the vector analysis, they use t-test. Maybe they are looking for some comparison or some relationships between variables. You can run regression, or maybe you can run ANOVA based on the question, based on your research question. Okay, you need to select one appropriate test for your research question. All right. Okay. So this is a hands-on example. You can do it at home. Okay, you can see that whether how much of the variance in actual sharing scores can be explained by the attitude score. So this is the research model, meaning that our attitude is our IV is our IV over here, and our actual sharing is our DV here, okay? Once you run, you should get the same output like this, okay? You go to material to data set, you use this data set, and then you can see over here, this one, R is just, simple correlation, which is a Pearson correlation. R square is coefficient of determination. You can look at the ANOVA table. If it's significant, we can conclude that yes, it is significant. There is a significant association between the two variables, okay? And then, and how do we interpret our the values of our R square? Last time we have already seen the values of R. Remember the correlation one? But this one is R square. If your R square is less than 0.12, meaning that it's small. If your R square between 0.13 and 25 is medium, and if it's greater than 0.26, meaning that your R square is large based on Coulthard. Okay, you can refer to this citation. Okay, and this is how you can report your linear regression. A simple linear regression was calculated to predict sharing the information based on attitude. A significant regression equation was found like this. Okay, you can report like this. With the R square of 36.7%, participants predicted sharing information is equal to this. This is the equation, okay, of our sharing information based on attitude. Okay, based on our attitude. This one is the constant I got from here, and this one is a coefficient I got from here, and times multiply by attitude. Okay, so that's all about our SPSS. We have discussed, about our SPSS. So just for your information, there are two generations of data analysis. SPSS is among first generation. Okay, is among first generation, but there is another generation of data analysis, which is a structure equation modeling, or SEM, or what we call SEM, right? SEM is not a statistical technique. It's not only one statistical technique. It integrates a number of different multivariate techniques into one model fitting framework. It is an integration of measurement theory, factor analysis, path analysis, regression, and some simultaneous equation. Let's say you have 3 IV, you have 3 DV. Okay, you have six continuous variables. You can easily use SEM in order to test your model, okay, instead of using, many times performing your regression. Regression is also good, it's not bad, okay? So a structural equation modeling allows to make use of several indicator variables per construct simultaneously, which leads to more valid conclusions on the construct level. Using other methods of analysis would often result in less clear conclusions and or would require several separate analyses. So SEM can be used to examine the effects of the variables and the relationships in the model simultaneously. In SEM models, each latent construct, as you can see here, the blue color one, each latent construct is modeled by the respective indicators. You can have, as in the case of this example, you can have a second order factor at the same time. The second order factor over here, you can have 2 mediators and you can have 1 IV. Okay, so it can be easily run in PLS. This one is part of PLS. Okay, so thanks for attending this session.